Well, class, we are now in section 8.5. We're going to talk about power series today. And you've seen a power series already in one of your homework problems. And basically what you've learned now in the first, the sections 8.2, 8.3, and 8.4 is you've learned about different kinds of series, and you found ways to determine if the series converge or diverge. And ultimately, we want to apply this knowledge of series to functions that have variables. In other words, like take the sine function. Could the sine function be written as a series? Okay. Could the cosine function be written as a series? Okay. Well, if they could, and they can, we call them power series. So what is a power series? All right, well, let me go down here a little bit. All right, so a power series is a series of this form. So you see, it's a summation, it's an infinite series, but the terms have the variable x in them. The terms have the variable x. So we call that a power series. The C sub n's are the coefficients of the series. And if we fix the value of x, for this series above would be a series of constants that we can test for convergence or divergence. A power series may converge for some values of x and diverge for other values of x. If we were to write the terms of the series out, well, the sum of the series actually is itself a function. That's what they're showing in this line here. I mean, the power series can be expressed as a function, believe it or not. A function like the sine or the cosine or the exponential function can be written as a power series. And it would be legitimate to take a function and express it as a power series and it would be good for the set of all x values for which the series converges. Okay, so this is the idea. Now, a very simple power series is, let's suppose we set all the coefficients equal to 1. Okay, let's suppose we set all the coefficients equal to 1. Well, then that power series above, that function f of x, or, well, I mean, actually, let me go up higher. This series here, this power series above, could be expressed then specifically as this series. You see, if you determine the values of the coefficients, then you have a specific power series. And in this case, the power series with all the coefficients in the power series were equal to 1, that series would equal 1 plus x squared and so forth. And that is a geometric series. A geometric series with a common ratio equal to x, and that series would converge when x is between -1 and 1, because that means the absolute value of x is less than 1. And the series will diverge when the absolute value of x is greater than or equal to 1. So again, a convergent geometric series converges when when the absolute value of its common ratio is less than 1. So that's an example of a series. And power series arise in mathematics a lot. They come up in all kinds of, like, physics and engineering. There's a famous series called a Bessel function, for instance, I'm trying to think. It can model, for instance, vibrating rubber membranes. They talk about that in the textbook a little bit. But let's go ahead. So power series, just like any series, what is interest of us is, of course, where the series, for what values of x does the series converge. Okay, and we can actually use the ratio test to help us determine this. So let me go right to an example here. Okay, and I want to give you a moment to copy down this example. Okay, take a moment to copy the example down. Okay, so here's our series. And let me see, let me plug my stylus in here. Hold on. Okay, so we want to find two important things. Okay, we want to find an interval of convergence and a radius of convergence for this particular power series. Now we're going to learn that this power series is actually a power series for some function. But we're not going to get into that just yet. We're going to get into that on when we talk about section 8.6, where we represent functions of power series. We'll start that discussion. For now, what we're trying to do is just determine where the power series converges for what values of x. Now, does this power series well, what we can do, what's your favorite convergence test so far? I'm just going to ask this. You've learned a lot of different types of tests you can use for convergence, but like alternating series test, ratio test, you know, a variety of examples, right? Integral test, comparison test, so forth. But what's kind of one of your favorite tests? I'm going out on a limb here, so to speak. I want to see what response you give me, being that you know that you've worked on section 8.4. Clea?
My favorite would say it would be the geometric series and the P series test. I feel like those are the most like easy ones for me and like they make the most sense to me.
Okay. Well, all right. And let me ask you this: if the series is complicated,
Mm-hmm.
what test do you think might be your favorite test? Let's say the series is, you know, somewhat. Let's say it's not a P series, not a geometric series. Let's say it's some series, and you want to analyze if where it convert, like if it converges or not. What? Okay, I see Susanna is mentioning the ratio test.
Yeah, me too. Or
Right. All right. Well,
either
you know what? You're in luck, everybody, because we will use the ratio test to determine where power series converges and where it diverges. So, so Suzanne, I'm sure is happy about that, and Claire's happy. Let's go and look at the solution here. So think of this as a series. The only difference is you have a variable x in it. So it's a power series. Okay, so well, first of all, what I'm going to do, I'm going to just expand the series out with some terms, okay? Just so, it makes it a little more intuitive. What is this power series? What is this power series? Well, it's just a series with a variable x in it, okay? So when, let me see here, when n equals 1, this is the term. When n equals 2, you get another term of the series. When n equals 3, you get another term of the series. And then you get the series. So these are just the first 3 terms of the power series, but we could keep going. But what we want to know is for what values of x this power series converges. So let me give you a moment to copy that down. Okay, are there any questions before we move on here?
Professor, I know this is a power series, but since we also have the minus one in front, will this also be called an alternating power series?
Well, it's an alternating series. I don't know. No, power series is sort of a very general term, but it's definitely an alternating series.
Okay.
And what does the series resemble? I mean, if you think about all the functions you've learned, trig
Mm-hmm.
functions and all kinds of, what does this power series resemble?
Well, it's a mechanism on how to get the
I'll
series.
give you a hint. It begins with a P, O, L,
Poly, polymetric?
poly, almost there.
Oh,
Polynomial.
polynomial.
That's right, OPME. That's right, Jonathan. So you see, power series, well, I got to be a little bit careful here. Well, no, I mean, it resembles a polynomial, right? It's a polynomial with an infinite number of terms, but we like polynomials. They're easy to work with. So if we can express some complicated function as a polynomial, that's nice. And that's like our goal, but that's a future goal. Right now, we're focused on where this power series converges for what values of x. So, okay, we'll move forward then. We're going to use the ratio test. We're going to use the ratio test. So remember what the series was. Maybe I can write it here. Hold on here. -1 to the nth times n squared times x to the nth all over 2 to the nth power. So this here is a sub n, right? So this is just, I'm putting this separate, of course, but that's how I get the a sub n here. I mean, you know, your series this is the general form of a series right here. And so your nth term is -1 to the nth power times n squared times x to the nth power over 2 to the nth power. And what we're going to do is we're going to use the ratio test. So the ratio test here, we're gonna look at the ratio of the n plus first term to the nth term. And we're going to look at the limit of that ratio as n goes to infinity. So here, well, sometimes it's easier, right, to, in the bottom you have the nth term. And then in the top here, the top fraction is the n plus first term. And you get that, as you know, just by replacing all the values of n in the nth term with n plus 1. We're taking the absolute value of that ratio, and a fraction divided by a fraction is a fraction multiplied by its reciprocal. And that gets us down to here. Okay, let me give you a moment to catch up here. Okay, so what I like to do, as you know, is I like to group like terms together. That's what I've done in this step. And then I do my simplification down here. Now I've not taken the limit yet, but you know, before I take the limit, I want my expression, my ratio of the n plus first term to the nth term to be as simple as possible. Please let me know if you have any questions, okay? Please let me know. What happens to the -1? Since we're taking the absolute value, what happens to the -1?
It becomes positive.
That's right, Clea. So okay. Are we ready to move to the next page so we can compute this limit? Oh, okay, Franklin. All right. Want to make sure I'm not going too fast. All right, Franklin, are you good? Okay, great. Okay, so we need to simplify this expression. So let's go ahead then. All right, so we're taking the limit as n goes to infinity. And of course, now this step here, I'll just highlight a little bit. You have these absolute values, right? Of course, n plus 1 over n squared, this term here, is always positive. So it can be moved out in front of the absolute value. But the absolute value of x minus 2, that has to stay inside the absolute values. We cannot bring the x out because x could be positive or negative. All right, and of course, this n plus 1 over n is like n over n plus 1 over n squared. And so you write that as 1 plus 1 over n squared. And as n goes to infinity, this whole thing here, this is just going to go to 1 squared. And so the limit will equal the absolute value of x over 2. Okay, and so by the ratio test, this power series here converges when the absolute value of the ratio, which is x over 2, is less than 1. We're applying the ratio test, section 8.4. It's just that our infinite series has a variable in it. But that's what we're doing. Yes, Clea?
So how can we know if it converges since we have a variable inside?
Well, we're not done yet. We have, yeah, for what values of x does the power series converge? Well, we know that if the absolute value of x, let me write, we know based on this statement here that if the absolute value of x over 2 is less than 1, the power series would converge for those values of x. So we need to solve this inequality to determine the values of x. So we're going to do that on the next page. We'll do that on the next page. We have to solve that inequality. Are there any other good questions? We're going to get there, Clea. Okay. Well, all right. So let's then go ahead and solve this equation, or I should say inequality, right? So the inequality is the absolute value of x over 2 is less than 1. Now, that means then that x over 2 is greater than negative 1 and less than 1. So just kind of a refresher here. Let's just say you had the let's just take a, let's say you had the absolute value of a is less than 3. Okay, and you have a number line This is your A number line. And, you have -3, -2, -1, 0, 1, 2, 3. Okay, so given that's the case, all the values of A between -3 and 3 would have to satisfy this inequality, right? Because the absolute value of any number between -3 and 3 would be less than 3. So you see, this implies that therefore that A is less than 3 and greater than -3. And you can see that, I mean, I think the number line geometrically shows it, graphically shows it, and then, you arrive here. Well, it's the same thing here. The absolute value, so we could further say if we had the absolute value of an apple, okay, less than, I don't know, 3, the apple would have to be less than 3 and greater than -3. Okay, so what I have here is I have the absolute value of x over 2 is less than 1. That means x over 2 is between -1 and 1. Are we okay with that? Are there any questions on that? Okay, well, what we can do, of course, is multiply through. I'm not squaring, I'm multiplying through. Let me clear this. I mean, this is all in the recording, but so we have x over 2 is less than 1, greater than -1. And I can multiply, sorry, hold on. I don't like my symbols getting too close. I can multiply through by 2 everywhere. But since 2 is positive, that doesn't change the inequality. So x is less than 2 and greater than -2. And so for these values of x, the power series will converge. The power series will converge when x is between -2 and 2. So like for instance, if I take this series, if I take this series here and let me give an analogy here. So let's say that x were equal to 1. If that's true, then our power series, so 2 is inside this interval. 1, I'm sorry, is inside this interval. 1 is between -2 and 2. If that's the case, then our power series becomes this power series. Hold on. becomes that power series. Now I'm looking at one thing here. So you see what I did? What I did was for x, I substituted in x equals 1. And I'm checking one thing out here. Right, right. Okay, so you get a series like this. That series converges. I know it converges because when I set x equals 1 here, x equals 1 falls inside my interval of convergence. So the power series, when I substitute x equals 1 in there, I end up getting this interesting series, and I know that series converges. Okay? All right, now we know that the series converges for all x values between -2 and 2. Are there any more x values where our power series converges? I mean, we got the whole, the whole number line, all the x values from -infinity to infinity. How can we be sure that we have all the values? Well, if we, let me see here. We have to really check now, you see, because I want to say this the right way. Let me go to the whiteboard. So our power series converges okay, when the absolute value of x over 2, which is L, is less than 1. And that means that x is between -2 and 2. This is by the ratio test, right? Now, similarly, the power series will diverge when the absolute value of x minus 2, which is L, is greater than 1, right? So the ratio test, you deal with in the limit a common ratio. If the absolute value of the common ratio L is less than 1, for those values of x, the series will converge. If the absolute value of the common ratio on the limit is greater than 1, for those values of x, the series will diverge. Well, all right, so over here, just kind of separate things out. If you have, I want to say this the right way. Yeah, this is fine. If you have the absolute value of x over 2 is greater than 1, that means that either x would have to be greater than 2 or x would be less than -2. Okay, in either case, I want this to be just a little bit neater. In either case, if x is greater than 2 or x is less than -2, then this this is satisfied. This is satisfied. Let me put in a little more detail here. Let me put in a little more detail. One moment. It's worth doing. Hold on. We're gonna need just a little more space. Okay, let me do this again. So, yeah, if the absolute value of x over 2 is greater than 1, think of it like that's the absolute value of x divided by the absolute value of 2 is greater than 1, which means the absolute value of x over 2 is greater than 1, which means the absolute value of x would be greater than 2 if you multiply by 2 both sides here of the inequality. If the absolute value of x is greater than 2, this means that either x is greater than 2 or x is less than negative 2. So this means the power series diverges when x is greater than 2 or x is less than negative 2, right? So now we have information about some other x values. So you have this piece of information, okay? And you have, so the series converges over that interval, and the series diverges for these values of x. Well, what values of x are left? You know, what values of x are left? That's right, Yonatan. What values of x do we need to study? Well, x equals 2 is 1. And what's the other x value? X equals 2 and x equals so the ratio test gave us information, right? It gives us information about convergence or divergence of our power series over different x values. Our power series converges when x is between negative 2 and 2. Power series diverges when x is greater than 2 or x is less than negative 2. So what values of x do we need to worry about that we haven't covered yet? What values of x does the ratio test not give us any information about? That's right, Yonatan, 2 and negative 2. So we need to determine convergence or divergence for those values separately. We're not done yet. We're not done yet. So this is what I've been saying. Okay, so I mean, basically the ratio test at x equals negative 2 or positive 2 would give you, in the limit, a ratio equal to 1. And that's where the ratio test gives no information. Okay, so we're going to have to go and check. We're going to have to check manually the values of x equals negative 2 and 2. We're going to have to plug those values in the series and see what happens. How many tried using the ratio test over the weekend in their homework and got like a non-informative ratio test? In other words, your ratio in the limit was equal to 1. How many did that happen to? How many of you? No? All right, well, let's go ahead now and check at x equals -2 and x equals 2. Let's check how the power series behaves for those x values. So we'll do that. Yes, Clea.
So, we still haven't determined if it converges or diverges, right?
We don't know at x equals -2 or x equals 2 if the power series converges or diverges, because the ratio test gives us no information for at those x values. We have
I
no
see.
information. So what we have to do is we have to actually physically go in, or manually, I should say, go in. Let me put this font back a little bit. And you see what I did here at x equals -2. Okay, you see how at x equals -2, I plug in x there, x equals -2, and I plug it into the series. And when I plug it in the series, I can reduce terms. And, so the -1 to the nth power times -2 to the nth power, well, I'm just rearranging terms here. And I simplify the series till I get to the summation of n squared. But that's going to diverge for the test for divergence. So that's what you have to do, Clea. You have to test your endpoints. We call those your endpoints. You have to test your endpoints that the ratio test doesn't give you information about. We have to test those for convergence or divergence. And at x equals -2, the power series diverges there. But at x equals and now at x equals +2, when x equals +2, we substitute in x equals +2, and of course something nice happens here. Make this thin. Something very nice happens here. We get a little bit of simplification, and we're left with the series. It's the alternating series, -1 n squared right here. But that series also diverges by the test for divergence. -1 squared plus 2 squared minus 3 squared plus 4 squared and so forth. That series is never going to settle down. And this is what you have to do for these problems that you're going to see from section 8.5. Are there any questions? Any questions on that?
Professor, I have a question.
Yes, Nia.
In the first step, we had a -2 to the power n, but the one after it, we have a 2. How did we lose the negative sign?
Oh, up here for the first one?
Yeah.
Well, so up here, the -1 to the nth power times -2 to the nth power is just -1 times 2 raised to the nth power. And so that gives you this 2 to the nth power here. If you
Okay.
have,
I see.
yeah, there's a to the nth power times b to the nth power is equal to a times b to the nth power. All right. Okay, are there any other good questions? That's right, Jonathan, that's right. They share the same power. Oh, and then by the way, of course, nice things happen here, right? Nice things happen. Put that n back in, hold on. Nice things happen because, hold on. Those 2 to the nth powers simplify out. Simplify out. So neither of the endpoints does the series converge at, power series. And so now we can say what our interval of convergence is. It's the open interval from -2 to 2. And I drew a picture below of an open interval from -2 to 2. I guess technically I should probably, put x here, right? X-axis. And the radius of convergence is just half the distance of your interval. So the interval down here goes from -2 to 2. The radius of convergence is, so that's a distance of 4. So the radius of convergence equals 2. Really, it's the interval of convergence that's, to me, more important. But, they like to talk about radius of convergence as well.
So, Professor, if it was from 0 to 3, the radius would be 3, right?
If the radius of convergence were 0 to 3, then, well, normally we get the interval of convergence, and then from there we can determine our radius of convergence, because the radius of convergence is always half the length of your interval.
Oh, I see.
Yeah. Yeah, that's right. That's right. Let me show you another one from the book here. I'm going to look at this example 1. Well, hold on one moment. Are there any questions at all with this example? Jonathan, we would say the length of the interval is 4. But of course, what's important, really important, is this interval. So we're saying that power series converges, our power series converges when x is between 2 and -2, and that's it. Power series is no good anywhere else. We're not going to use the power series for values of x that diverge. We're going to use power series for values of x that converge. So we would get a finite sum. So, but yes, the length of the interval is 4. The radius of the interval of convergence is 2. Let me look at one more with you here. I want to look at one more before we go on break here. Hold on. This is actually example 1 from the textbook. So in example 1, they talk about a power series that, in this case, converges only at its center. So for what values of x is this power series convergent? Okay, and I want to look at that in the whiteboard for a moment, because you see there's a factorial there, and sometimes students with factorials, it makes students a little bit nervous, but there's no need to be nervous. No need to be nervous. Okay. So let me see here. I always have to put that font back. Put it back. There we go. So this is example 1 from in section 8.5. And here's the power series. Starts at n equals 0 to infinity of n factorial times x to the nth power. So the ratio test, you take the n plus first term to the nth term. The nth term, of course, is n factorial times x to the nth power. The n plus first term would be n plus 1 factorial times x to the n plus first power. Now, n plus 1 factorial, okay, n plus 1 factorial, this here can be written as n plus 1 times n factorial. Okay, that's going to be necessary for this problem. It's like if you had 3 factorial. 3 factorial is 3 times 2 times 1, right? 4 factorial is 4 times 3 times 2 times 1, but that's just 4 times 3 factorial. Okay, so n plus 1 factorial can just be written as n plus 1 times n factorial, just like 4 factorial was equal to 4 times 3 factorial. And this is going to help you simplify it, simplify the expression, because you'll have n plus 1 times n factorial over n factorial times n to the x plus first power over x to the n. And there's going to be a lot of simplification going on here. The n factorials simplify out, and you're left here with what? N plus 1 times x. Hold on. N plus 1 times x. But the n plus 1 can be brought out in front of the absolute value. So you have n plus 1 to the absolute value of x. But this will equal infinity as n goes to infinity, okay, for all x values except, one moment. Okay. It'll equal infinity as n goes to infinity for all x values except x equals what? What one x value would this, yeah, 0, except x equals 0. Okay, so some of these problems you'll have to deal with factorials, and they're not hard to deal with. This is traditionally how you do that. So that's right, Yonatan. At x equals 0, the series, the limit will not equal infinity. As a matter of fact, it will equal 0. So if we go back then to the example, the first example from section 8.5, now what they're saying here, hold on, now it makes sense. Okay, and let me just see one more thing. Hold on. Yeah. Yep, that's right. That's right. Okay, it makes good sense now. So this series diverges when x is not equal to 0. So this series converges only at one point at x equals 0. Not very interesting, but you know. So are there any? We're going to do another example. We're going to do another example. But do you have? I want us to take a little break, and I got to get the homework posted for Wednesday for you, and I'm going to do that. So let's take like a 5-minute break, and and then at from 5:15 to 5:30, you can work on your new homework section for section 8.5. I have to get it posted. Give me just a few moments. Are there any questions before we stop the recording here? Okay, let me stop the recording.